Okay, folks, so it's time for us to start the last presentation of the morning session. Take it away.
Okay, so can you hear me well? Good. So I'll present CINABRO. It's a software-driven open flash array architecture for scalable cloud storage services. I'm from a startup company, Blvd, out of Sunnyvale, California. Before we begin with the motivation, I'd like to comment on a new industry initiative announced yesterday by Microsoft. It's called Denali, and it's based on open channel SSDs for new type of flash memory storages. Our technology and product is also based on open channel SSD interface. So it's exciting to see that open channel SSD technology is getting a new momentum. For motivations, we like to solve two problems. First, it's hard to meet diverse cloud storage requirements with existing flash storage architecture based on conventional SSDs. Typically, data center SSDs typically run 3 to 5 years after rigorous qualification process. Due to this expensive validation process, and for some other reasons, it's hard to upgrade SSD firmware just to meet new workload requirements. Second, we like to streamline flash memory deployments in scale at data centers. Oftentimes, NAND modules inside latest storage appliances and SSDs are not necessarily the latest flash technologies. The component obsolescence problem shown in this figure describes this particular problem in generic terms. We aim to enable fast deployment of the latest and the greatest NANDs, for example, within 6 months of their first product availability. This is our solution. Our solution will facilitate lowering total BOM cost by leveraging simpler SSD device architecture. We can remove onboard DRAMs from the SSDs. We can also remove power loss protection capacitors from SSDs. Instead, we can rely on backed up host power and pooled DRAM in host memory. Also, much of the intelligence that used to run on the SoC onboard SSD, those intelligence can be shifted to host CPU and run in the form as a host software. This will also help cut the cost on SSD controllers. In the table, you can see some potential cost-saving opportunities. This is a more detailed view of our CINABRO flash array architecture. This architecture is based upon off-the-shelf data center server architecture. Application nodes typically access the box over NVMe-oF fabrics. Dozens of SSDs are accessed through OCSSD or Open Channel SSD interface. I will explain OCSSD interface in detail in the next slide. CB Bridge is our SSD controller, and CBOS, or CB operating system, is our host software stack running on the host server CPU. So for the NAND flash interface, we are using OCSSD. OCSSD interface is based upon standard NVMe protocol, but it allows host a direct access to flash memory. In our flash array system, CINABRO, the SSD SoC typically only handles the flash media management, such as ECC data protection. All the other upper layer management functions, like data placement, I/O over provisioning, and garbage collection, run as host software. We believe OCSSD-based design has advantages for flash usage in data centers. Latest NANDs, such as 3D TLC, and future products like 3D QLC, is highly complicated. By having SSD controller hardware focus just on handling this NAND complexity and having host software handle relatively logical and media-independent functions, we can achieve faster deployment of the latest NANDs and also can quickly adapt to dynamic and diverse data center workloads. This is an overview of CB Bridge, our OCSSD optimized SSD controller. CB Bridge implements robust and high-performance NAND media functions. It'll handle all the standard OCSSD features and additional features for close lay optimizations, working with host hardware and host software. It'll be based on 28 nanometer process and will be able to accommodate 96 or higher layer 3D NAND with LDPC data protection schemes. On the SoC diagram, we can see blocks for host control, buffer control, peripheral control, and flash control. The CPU, the onboard CPU, just needs to be powerful enough to coordinate these blocks. Also notice that there is no DRAM interface in our SoC design. For network interfaces to our flash array box, we will use NVMe-oF fabrics. NVMe-oF fabrics provides near local storage latencies over network links. Our composable array design can accommodate various transport types of NVMe-oF fabrics. This includes hardware-accelerated Ethernet transports and software-only implementation of TCP/IP transport. Furthermore, new system and network technologies like SmartNIC, FPGA acceleration, software-defined network methodologies can be integrated with open channel SSDs in a seamless fashion. We base our host software stack on various open source software packages. You can see the list. The list includes Linux and SPDK. SPDK is Storage Performance Development Kit, and it's an open source software. It allows user-level implementation of storage and flash array functions. Host-managed array FTLs typically run on top of user-level drivers to manage array of NANDs in a scalable manner. Host software leverages multi-core and multiprocessor CPU to achieve high parallelism. We also use Linux containers and Kubernetes to blend in with the existing data center software workflow and practices. This is a CB operating system diagram. You can see multiple host software modules. The modules include host-based array FTLs, system resource and performance manager, flash management, and storage management modules. Most of these modules run inside containers. The host-based flash array FTLs, it typically come with multiple library to pick and choose from to optimize for specific workload characteristics. For application interface, basic mode is to access volumes of open channel SSDs defined by these host FTLs through NVMe-oF fabrics protocols. So in this case, we will basically exposing multiple logical volumes to NVMe-oF fabrics hosts. If the configuration allows more host processing power, then applications basically send their application plugin containers to the CINABRO storage node to do some plugin functions. So you can send, for example, RocksDB or Ceph application modules, and they will run as containers, and they will access our open channel SSDs using local block device interfaces. This example shows how CBOS containers run storage functions and accommodate application plugins. This example is constructed just for the description purposes, and it's very simple with 2-socket and 4-core CPUs. As you can see in the bottom of the diagram, each CPU core handles 8 OCSSD units, and each socket handles 1 NVMe Fabrics NIC card. Following the SPDK open source framework, each core accesses OCSSD and the NIC card with basic PCIe and RDMA driver in the kernel space. Other than that, all the device, storage, and application logics are implemented in the user space. On CPU 0 core, we have SPDK's NVMe Fabrics target running on top of block FTL-A type host FTL. It will expose all OCSSDs from number 0 to number 7, and these IOs will be exposed to the network side through network interface card number 0. If CPU 0 has remaining power, CBOS can schedule managerial tasks like system resource and performance manager. Similarly, for the other cores from CPU 1 to CPU 3, different types of FTL libraries are incorporated to support diverse workloads over arrays of open channel SSDs. So far, I gave the overview of our CINABRO flash array architecture. I'll now talk about our current prototype implementation status and our plans. So let me first play a video clip that explains our working prototype. So our working prototype is based upon a off-the-shelf server. It has 2 latest server-grade CPUs. It has 4 open channel SSDs. You can see in the bottom, those 4 PCIe cards are FPGA-based open SSDs. The open SSD has silenced FPGA to be programmed as a SSD controller, and it can support up to 1 terabyte of NAND. We also use a NVMe Fabrics NIC card for NVMe Fabrics traffics. The graph shows initial performance measurement. As number of OCSSDs increase, you can see the linear increase of the throughput. Red and blue bars represent 2 different versions of host FTLs that we implemented. Now we see this container-based video server demo. So we have 2 Kubernetes worker nodes, one for NVMe Fabrics target, the other for video server. We also have Kubernetes master, which coordinates the NVMe Fabrics target and video server. We built a simple web-based video server just to verify the correct operation of this video server application running on top of our host FTL NVMe Fabrics targets. So you can see all the videos are being played smoothly. This particular configuration is running on top of 4 units of NVMe Fabrics targets, but in the other configuration, we used up to 24 units of emulated open channel SSDs. Because we are using standard Docker and Kubernetes technology, you can see the current status of this deployment and resource usages using standard Kubernetes dashboard. So Phase 1 is our working prototype, which has very basic, but also at the very crucial functions in NVMe fabrics and some of the host FTL implementations. For phase 1 and phase 2, we are using what is called Cosmos Open SSD, PCIe cards. It is the FPGA-based SSD development platform. And OpenSSD will be mainly used for our physical SSD device until phase 3. So phase 3 is our final design for CINABRO flash array system. We will have OCSSD optimized CINABRO bridge, CB bridge SoC. With this, we will have compact form factor SSDs. The phase 3 design will also come with optimized PCIe fabrics and feature-complete suite of host software. In parallel with this product development, we will contribute parts of our software and hardware to open source community. Today, we have committed codes in SPDK. So it's a part of the official release version 17.10 and 18.01. These codes enable SPDK access to open channel SSD hardware. Later this year, FPGA RTL code will be open sourced. Developers will be able to modify or develop new features on top of this OCSSD RTL codes. Also, we will share our SPDK user-level software that will work with this OpenSSD hardware platform. Next year, we will open source more software and hardware components. This is our current lab setup, consisting of a few Cosmos OpenSSD FPGA cards, a number of off-the-shelf servers, and number of high-speed Ethernet for NVMe over fabrics. This diagram shows how our host FTLs are implemented. Our host FTLs are implemented in the form of SPDK's BDEV. SPDK BDEV is a block device and allows virtual BDEVs to be stacked on top of either physical device BDEV or another virtual device BDEV. For example, in the diagram, you can see BDEV layer called LNVM BDEV. It's a virtual BDEV that bridges OCSSD hardware and logical block devices. Our first FTL, UBM, it provides a very simple logical to physical block mappings. It also provides data stripings. Our second FTL, called GFTL, it implements page mappings and garbage collections in addition. Also, another important feature that we are using out of SPDK is its NVMe fabrics feature. SPDK allows any block device to be exposed as an NVMe over fabrics target. This powerful feature allows us to evaluate virtually any application on the NVMe fabrics host side or application node side. Because on NVMe over fabrics host side, where applications typically run, we'll recognize our host FTLs as nothing but regular Linux block devices. Currently, our application evaluation setup is either based on 4 units of physical open SSDs or virtualized OCSSDs up to 24 instances. In addition to the video server prototype and evaluation, we have completed basic benchmark tests with official RocksDB releases. It was done over NVMe over fabrics remote drives. We also did a similar test with SPDK's RocksDB plugin. We are also engaging with an external partner in SK Telecom, one of the major telcos in Korea. We are jointly performing integration tests of the all-flash SF. All-flash SF is from SK Telecom, and it's a flash memory enhanced version of open source SF software. So to summarize, our solution has benefits in quickly deploying latest NANDs from multiple vendors. It's also accommodating multiple generations of NANDs. Another benefit is quickly adapting to diverse data center workloads. Finally, as most of the storage intelligence is implemented in host software, it is easier to implement flash array functions. Our work has been contributed to OpenSSD RTL codes, OCSSD standards, and SPDK software. For OCP, we are open to collaboration ideas about making some of our hardware design available. You can find some other resources in the following links, and thanks for listening.
Any questions?
So you tie a specific application to it? SPDK runs in user space, so you tie a specific application to it? Or
we are not targeting specific applications, and I think that's the beauty of this architecture. You can actually come up with a new host FTL if you have a new types of workload, because you can all develop in software layer. Not all, but chunk of intelligence in the software layer.
So from your solution perspective, I see that NVMe fabric target as your one of the sweet spot. That definitely you can build NVMe fabric target. But when you go into each and every application, like you're talking about Ceph, you're talking about RocksDB, running right on your platform itself, then it becomes a problem of how do you size your platform? How do you make that? Are you targeting all sorts of things, or are you targeting a specific kind of, like for NVMe fabric? No brainer, you can do that.
So we will start supporting NVMe fabric's target model, and we will probably start with popular applications.
Got it.
Yeah.
Because I see that RocksDB, you're running agent for RocksDB, you're running agent for Ceph.
Yes.
That's a very complicated problem to solve in the market, at least.
Yes.
So you mentioned NVMe over Fabric. That requires scatter-gather list support. Where is that implemented?
Scatter-gather list support. I think our SoC will be able to handle SGL type IOs. So it's built on the SoC. But
that would be in the SSD or in the bridge?
In the CB bridge.
In the bridge, okay.
Yeah, it's capable of doing SGL type IOs.
How do you do it today, though? You don't support SGL today.
Not today. You saw our prototype. It's built as a FTL FPGA SSD. We don't have that today.
But in the future, it'll be in that SoC.
Yes, we are planning to support SGL IO.
Any other questions?